So this is RMI's Limestone Calcined Clay webinar focused on practical applications for departments of transportation. So what we're really interested in doing today is educating on this emerging blended cement product and discussing with you all and co-creating some ideas for how we can start to pilot and demonstrate this product at DOTs across the country. So our agenda for today is we'll have some presentation up top where we'll introduce LC3, provide some information about this material, and then we'll have a speaker talk about some of the performance characteristics of the material from their research, and then have a discussion about how practical application at state DOTs would work. And then we'll spend the rest of the hour in a more interactive session. So we'll have some audience polling. So we'll have questions just to crowdsource some information. And then we'll have a discussion about barriers and solutions, really driving towards some really immediate next steps or action items that you can leave this meeting with to take to your current role. So our speakers today, my name is Anish Tulak. I'm a manager in the Carbon Free Buildings program at RMI. I work on our Embodied Carbon initiative. I'm joined by my colleagues Audrey Remfer and Jackie Rice. And I'm pleased to introduce you to our guest speakers, Tom Van Dam from WJE Associates, and I'll let Tom provide a more detailed intro when he's up, and then Oljan Sandbeck from GCP Applied Technologies. So thanks to those guest speakers for being here today, and yeah, we'll just dive into the content. So this is just a bit of introduction on why we're focusing on cement so heavily for this discussion. And this is, redundant information for many of you, but concrete is the most widely used man-made material today, and it's second only to water as the world's most consumed resource. And when we look at the component parts of concrete today, ordinary Portland cement, OPC, is the major component of concrete and really the driver of its environmental impact. And so thinking about how we can reduce the use of OPC with other materials is really a goal to reduce environmental impact. Where is the embodied carbon in cement? So if we're targeting OPC as the major source of the environmental impact within the production process of cement, it really comes down to the process emissions. And so 85% of total cement CO2 emissions come from fuel usage for kilns and preheating, but more importantly, the actual calcination process of turning limestone input into cement and clinker. So reducing the ratio of clinker is an important element to reduce the environmental impact of cement and thus concrete. So we're here today to talk about LC3. LC3 stands for Limestone Calcined Clay Cement, and it's an innovative blended Portland cement product that includes the addition of metakaolin, which is a calcined kaolinite clay, as well as some amount of limestone. So on this graph, what you're seeing is a more typical OPC, which is 95% clinker, 5% gypsum. This is illustrative, so we know that this could vary based on the exact product. And then on the right, that right bar is really showing what the environmental impact or carbon impact of that material is. So you can see that the clinker is driving emissions. How does LC3 compare? So in LC3, we're reducing the clinker ratio considerably. We are including calcined clay as an additive, and we're also including 15% limestone. And that you can see on the far right, how that results in a significant reduction in the thermal energy that's needed to produce this blended cement compared to OPC. So the value of using LC3 is that it is good for the climate, it has cost benefits, and it has performance benefits, or at the very least performs comparably to OPC and other blended cements that DOTs are used to using. So it's resource efficient, carbon efficient, and domestically available. And calcined clay and limestone are already commonly used as CMs today. The major innovation in LC3 is that it's combining the use of abundantly available low-grade kaolinite clay with a further 15% limestone. And it's those component parts together that have kind of a synergetic effect that enable the blended cement to achieve a similar performance to OPC. And that's really the innovation here, and why we're really excited about this material and hope that to increase its use in the market. I mentioned the cost benefits earlier. LC3 production can cost to 25% lower compared to OPC production. And you can think about that in line with the climate benefits. So you're reducing the need for these really thermally intensive processes needed to produce OPC. And as a result, you have cost savings from just reducing the use of that cement. And then we know that there is less availability, or will be increasingly less available, SCMs that are commonly used today, such as fly ash and slag. And so there's a real need for DOTs to find cost-effective alternatives to reduce clinker in cement and thus reduce environmental impact. So LC3 provides a really great opportunity because it is a very widely available, like the clay is a very widely available source material. So this product has the potential to scale very dramatically and offer a more consistent source over time. And these are some charts on the performance benefits of LC3, just comparing it to OPC, which is the gray bar. So you can see OPC here, compressive strength on the y-axis, and then just different days after pouring. And you can see that these different permutations of LC3 offer comparable strength over time. So maybe not day one, but certainly within 7 days and then beyond, providing the performance that is comparable to OPC. And case studies are dramatically scaling. So you have a few examples here. This material is commonly used in India and increasingly in Latin America as well. So there are precedents for the use of this product in different applications. And it's really the North American market that we are seeking to increase use, consumer confidence in LC3. And large cement majors in the US are scaling production for LC3 today. I know that's a big question folks have, is this material available? And there are large cement companies that are actively working on this. And I think from their perspective, they want to see increased acceptance, confidence, and demonstration from major buyers. So DOTs as an example, but also the building industry. And that confidence will accelerate the pace of investment in these technologies. So work like this to accelerate and build capacity amongst consumers is a really important piece of the puzzle. So if you have questions about the availability of LC3 or future availability of LC3 in your region, you can contact me or anyone at RMI, and we can have a follow-up discussion about that. So with that, I will turn it over to Olcan, who will speak a little bit more about some of the performance parameters of LC3 from his research. Go ahead, Olcan.
Yeah, thank you, Anish. Hi, everyone. This is Olcan Canbek from GCP Applied Technologies, a Saint-Gobain company. I will present some of my PhD thesis results that I did at Georgia Tech under the supervision of Kim Curtis. Maybe some of you are familiar with her. Yep, we can go ahead. So yeah, Anish already mentioned, and he went through this figure on the left, comparing LC3 versus Portland cement, but I'll also give a brief introduction for LC3. So it's a mixture of Portland cement, limestone, and calcined clay that can reduce the CO2 emissions between 30 and 40% in the concrete industry, according to the projections. And so why LC3 is a viable option can be explained by the availability of supplementary cementitious materials in the field. This availability of SCMs is summarized in the figure on the right. So you can see like all the SCMs that we have right now in the SCM, like most of them are in this figure. For example, silica fume, fly ash, slag, clays. The good news about the clays and limestone is that they are not as used in cement as they are for example, blended cements, including fly ash or slag. But we have lots of reserves for clays and limestone, which makes LC3 a good option for the future. And considering like retirement of some of like the coal power plants, coal-based power plants in the US and in other countries, that will decrease the fly ash supply. We may want to consider LC3 for the future. So in one of the studies I did in my research was, okay, LC3 looks good in laboratory in terms of the performance, but the transition of LC3 from laboratory to field, we know that is going to be highly dependent on the ability to formulate it with respect to both performance and sustainability. So the question was, okay, can we optimize LC3 with respect to performance? And I mean compressive strength, development by performance, and sustainability from point of view. And this sustainability, we quantified it by calculating global warming potential in CO2 equivalent kilograms per binder. So the methodology I followed was varying LC3 composition from many angles. For example, you can formulate LC3 by varying Portland cement, calcined clay, limestone mass proportions. Also, you can vary the particle size. For example, I also vary limestone particle sizes at 3 different levels. And with all this, I tested many LC3 paste cubes to do compressive strength experiments, and then also ran an optimization algorithm to understand the best LC3 composition in terms of both these objectives as strength and sustainability. So this figure shows how global warming potential of LC3 changes with respect to varying proportion of the components, Portland cement, metakaolin, and limestone, also with respect to limestone fineness. So just to summarize this, what I want you to notice is increasing the limestone content at the expense of Portland cement and metakaolin decreases the global warming potential of LC3. Also, the finer the limestone is, the higher the global warming potential. So because that requires a lot of processing, the grinding of limestone. So we want to keep the calcined clay content low as much as possible, Portland cement content as low as possible. Also, we would like to use coarser limestone to be able to achieve relatively lower global warming potential. But obviously, this will depend on the performance objectives and we have. So the lowest global warming potential in this figure was achieved, for example, with the mix 40-20-40, which means 40% Portland cement, 20% calcined clay, and 40% limestone, including the coarsest limestone I had in my experimental metrics, which was approximately 49% lower than global warming potential of Portland cement, according to our calculations. So the results show that, so yeah, we optimized it in two ways. We said, let's maximize the 3-day predicted compressive strength while minimizing the global warming potential as much as possible. And at the second optimization routine, we maximize the 56-day predicted compressive strength while minimizing the global warming potential. And you can see like these figures show global warming potential on the y-axis, on the x-axis compressive strength. The left one is 3-day, the right one is 56 days. And the data points are colored differently here with respect to the limestone particle size. L3 means 3 micrometer medium particle diameter of limestone. And similarly for the others, L15, L25, they are coarser. And the red circles show the Pareto front, which is the non-dominated, the best solutions reaching the objectives of high compressive strength, low global warming potential. And from the trends, so the algorithm came up with these LC3 compositions, so-called the Pareto fronts. And in the trends, we realized that the algorithm kept suggesting us high Portland cement and calcined clay contents to reach high early strength. But for late strength, it did not push using fine limestone or relatively higher calcined clay contents for 56 days. So in summary, for 56 days, the algorithm confirmed that, okay, we can use relatively coarser limestones and less calcined clay content than 30% to achieve. And we validated these results in laboratory. So the algorithm gave some compositions, and we selected some of them and tested in the lab. And we validated that the predicted compressive strengths were within 10% error rates with the measured compressive strength. And the second study I want to mention today is the correlation between surface resistivity and strength development of LC3 investigation I did during my research. And in this study, I varied LC3 composition with respect to Portland cement, calcined clay, limestone contents at 3 different levels. Varied the limestone particle size at 3 different levels. Also the gypsum, added gypsum, which changes the sulfate balance of LC3. Also a very important property. And I casted concrete cylinders, 4x8 concrete cylinders for surface resistivity measurements. And using the same proportions, I made mortar cubes according to the ASTM standard for compressive strength testing. So to briefly mention the surface resistivity test for those who are not very familiar with. So it's standardized like AASHTO experiment. You use a probe, so-called Venner probe. It has 4 probes. The outer ones send an electrical current. The inner ones measure the difference, electrical difference, and then it calculates the resistivity automatically. This device we have. So the higher the resistivity, the higher the tortuosity on your concrete you would expect. But that also depends on the pore solution concentration. So if you keep the concentration to conductivity constant, for example, you can say the higher the resistivity, the better the microstructure, as shown in this schematic. And this is my last slide. So after finishing these experiments, we realized that the LC3 concrete surface resistivity and mortar compressive strength have a strong logarithmic relationship. But this is within obviously our experimental matrix. But still, it's still very promising. We observed an R-square larger than 0.9. And we attributed the greater changes in resistivity after 3 days to the binding of alkalis in pore solution of LC3 by the main hydrated phase called cash. And yeah, in summary, LC3 compressive strength may be able to be predicted by a really fast, non-destructive, like an easy experiment called surface resistivity. Thank you for listening.
Thanks, Oljan. I'll hand it over to Tom. Go ahead, Tom, and you have 10 minutes or so. Go ahead.
Thanks, Anish. First thing I want to say is, Anish, you're going to have to get a new picture of me. That one is showing me as young, and I'm getting kind of old. Next, do I have control? I do, or not? Maybe I don't.
No, I'll do it.
Okay, excellent. I just want to start with this slide because I do think this is a centering slide, just to make us all focus why we're on this call. We can talk about climatic models. We can talk about hurricanes hitting Florida and heat waves in Phoenix, and sometimes that's not as compelling to some as just looking at the sheer data. And this kind of shows over the last 400,000 years where we've been with atmospheric carbon dioxide. Hit it again. Yeah, and this is actually measured data from Hawaii, starting in 1960, and one more click. And this is as of a couple of days ago. And, we will see little brief fluctuations in the parts per million of CO2 in the atmosphere, but the trend is decidedly upward and in a scary way. And I think that people lose sight of the fact when they get lost in the models. And, for me, I think the models are very important, but for others, they don't find them very compelling. But I think just the dramatic increase in CO2 that's been measured and is occurring should be of concern to all. Next slide. So I work a lot with DOTs and have for decades. I do a lot of work with various DOTs, federal highways, and others. And the one thing that is absolutely sure is that change is difficult. And for engineers that are responsible for the public's money and safety, it can be very difficult. So across the board, DOTs all over the country, their initial reaction to change is it's a difficult thing to do because with change comes risk, and then the question of who bears the risk. And so when we change something, who is responsible if something doesn't go well? Change takes time and considerable effort. DOTs are currently resource constrained, so they don't have a lot of resources to put towards this, and institutional barriers exist that are roadblocks to change. And these are codified right in our specs and design procedures, and also within institutional knowledge. And so we really have to combat this. Next slide. Within our state specs right now for cementitious materials, most states are dependent on like the AASHTO M85, ASTM C150 Portland cement specs, joined with, you know, the ASTM M295, ASTM C618 coal ash natural pozzolans, and then the corresponding specs for slag cement. Those are the most common specs you'll find. Most states also permit blended cements. And up until about 4 or 5 years ago, maybe, you know, 4 or 5% of cement production in the U.S. was blended. Today, we're up to close to 40%, almost all because of the adoption of 1L, or the production of 1L cements, in which we are intergrinding limestone. But you could also have slag cement, Portland pozzolan, or ternary blends. I bring this up because if your specs do allow a type 1T, unless you put stipulations on it, that would allow you to spec an LC3. So you could spec an L15 P35, for example, or P30, and you would have an LC3 cement. So within your current specs, not a big stretch. Next slide. Very few states and agencies allow for performance specs, hydraulic cements. These fall under ASTM C 1157. There's not an AASHTO equivalent, and they really focus on material performance versus material composition. The lack of material composition definitely makes agencies nervous. And yet some agencies have used ASTM C 1157 really as a gateway towards adoption of something like PLC, where the state of Colorado was a leader in adoption in the, you know, late 2000s. At that time, PLC was not under the ASTM C 595 spec. But even since then, Colorado has gone to pulling back from using ASTM C 1157. So that is a potential spec avenue, but not well utilized. Next slide. So what can a state or an agency do or follow to adopt an LC3? And so as I mentioned, the first things to do is look at your current specs, work within them, see if you do allow that ASTM C 595 type 1T, and that is one way to work within your current specs. If you don't have this avenue, you really can introduce the LC3 through a special provision, again, either based on the type 1T or an 1157. And then you could throw in some additional testing requirements, and maybe some other requirements like shrinkage, resistivity would be good things to look at. And then develop a specification with partners that then you could utilize. Next slide. The bigger question is, how do you utilize it? And it's really through demonstration. And demonstration projects, in my opinion, these allow you to look at a new material, to demonstrate their utilization, their applicability, and then to reduce the risks associated with being an early adopter. Credible demonstration projects must be significant. They must use existing equipment and facilities, and it must be a real project. And so basically this is talking about taking something like an LC3, bringing it from the laboratory, working with your supplier and contractor, get it through the concrete plant, and get it on grade if you're looking at a sidewalk, a pavement, something of that type. I think it's important that the project is significant. I think it's important that the project is visible. I also think for new things, we don't want to put them in critical locations. And so sidewalks, you know, starting at the DOT facilities is an excellent place to start. But then moving into pedestrian accessible areas where you can put signage up and talk about the story. It's really important to collect data and materials while you're doing these projects and collaborate with others, such as the National Concrete Consortium or the National Road Research Alliance. And if you have questions who these are, my email's available to you and I can fill you in. Next slide. So I do want to talk about some funding opportunities that are currently available. The FHWA has been given $2 billion under the Inflation Reduction Act. The EPA has made, I think, preliminary determination of what constitutes a low carbon, reduced carbon material, of which concrete is one of them. And there is going to be a program announcement, it sounds like sometime here in the next month or so, through a notice of funding opportunity. Basically, and by the end of the year, applications will be available. Programs will cover additional costs incurred to demonstrate low carbon materials. And it will cover all additional costs, not just the material costs. These costs are all of the engineering involved, all of the additional testing, the development of EPDs. Everything can be covered under this. And the ultimate goal in this program is going to be to change agency specs and practices. Next slide. So we have a team, we being myself and Larry Sutter, Doug Hooten, and Al Innes, some names that might be familiar to a few of you. Basically, we're creating a reduced carbon concrete consortium of agencies that basically help navigate this process towards the IRA money becoming available, and then through the application into actual success. So basically, the idea is to work in partnership to develop these applications to design and construct demonstration projects that can feature an innovative low carbon concrete material, such as LC3. We would be there to provide technical assistance throughout the process. And really, it's important that we collect data in a unified fashion, monitor performance, store materials for future testing, and disseminate that. Next slide. And so the final slide, I do want to mention, thanks is kind of bled out there. Thanks, that says, if you're subtly. Basically, eligible agencies are any that are receiving federal aid highway money. So if you're thinking about the IRA money, state DOTs, of course, are eligible. But if you are a local agency, a regional transportation authority, possibly even a mass transit authority that's receiving federal aid highway money for a project, those projects are available for that IRA funding. And so with that, I will turn it back over to you, Anish.
Thanks, Tom, and thanks for that great call to action for us all to work together to get this material and other low carbon concrete and cement products demonstrated and share knowledge amongst all these agencies. So that was great. I'm going to hand it over to Audrey, who will lead us through a little bit of live polling, just to take everyone's temperature on where everyone's at with this knowledge and this material. Go ahead. I'll stop sharing my screen.
All right. As Anish mentioned, we're going to do a quick live polling session. So this is going to require your participation, and you'll have to use this website called Menti. I've just dropped a link into the chat, or alternatively, you can open your camera on your phone if you have a smartphone and scan this QR code, which will take you to the polling website where you'll be able to enter your answers to the questions that we're going to show. So if anyone has any questions on how to access the live polling, you can come off mute and let us know you're having trouble, or type in the chat.
Yeah, and feel free to use that link in the chat. I think that should work pretty well. This QR code, I'm going to take it down and then hand over the screen to Audrey to walk through the polling questions. So give you one more chance to use the QR code. All right, I'm going to take it down. Go ahead, Audrey, and you can share slides.
All right. All right. So our first question is, what is your level of familiarity with LC3?
And if you're not seeing this question on your Mentimeter, at the top it should say go to slide, and that'll take you to this question. So folks can follow along with Audrey's slides.
Okay, responses are slowing down. All right. It looks like most of us have heard of it, but have never worked with it. But we do have somebody who has worked with it, and a few that haven't heard of it prior to today. All right. Next slide. Given what you know about LC3, are you interested in using it in a project? All right, it looks like answers have kind of trickled down. Oh no, we're still getting some. I'll give a couple more seconds. All right, looks like we're a majority yes. Our next question, what is preventing you from using LC3? Check all that apply. All right, it looks like we're kind of across the board on this one. All right. The next question, would current specifications allow for LC3 or would LC3 need product approval to be used in a DOT project? Right, answers are slowing down. It's looking like a majority will need approval or specification adjustment. Next question is, does your specification allow for AASHTO M240 or ASTM C595 blended cements? You can check all that apply here. All right. Looks like common for type ILIPIS. Some are able to spec IT. All right. What projects have you used AASHTO M240 or ASTM C595 blended cement on? So this is going to come up as a word cloud. You can just type in the type of blended cement, comma, the type of project with each entry, and you'll be able to enter up to 3 if you have worked with these on multiple projects. All right. Well, like, looks like a lot of people are able to use these blended cements on all projects, have used on air-filled pavements. For the sake of time, we'll keep moving forward. Does your specification allow for the use of ASTM C1157 performance hydraulic cement? All right, looks like the consensus is no here on this one. Nope, we've got some coming in on yes. All right, we'll move to the next one. This is another word cloud. So what projects have you used ASTM C1157 performance hydraulic cements on? You can type the type of project in each entry. You can have up to 3 entries if you've had multiple.
I guess if any of those 2 people who said yes on the last one have thoughts here, that would be helpful.
I'll give you a few more moments to, there we go. Flowable fill projects. Okay, for the sake of time, we'll keep moving forward. Another word cloud, and I believe this is going to be the last one. What type of project would be applicable for the first pilot of LC3? And you will have one entry for this one. All right, so we're getting some pavements. Foundation. Give you guys a few more seconds to type in your responses. All right, on structural. And we'll move to the next slide. Oh, I lied, we do have one more. What test results would give you confidence in the performance of the new cement? You can type up to 3 entries here. I believe this is our last word cloud. Okay, same performance as an IL. Freeze thaw, strength test, setting time, flowability, permeability, set time, shrinkage. Great. We'll give a couple more moments. All right. And that concludes our live polling. Thanks everyone for participating. I'm gonna pass it back to Anish and we're gonna move into our breakout groups.
Thanks, Audrey. I know we're running a little bit short on time, so we'll keep these pretty brief, but I think it would just be a good chance for folks to have just a brief discussion on some of the barrier solutions. And really what we want to come out of this meeting with is like a list of next steps, whether it's demonstration project ideas, things like that. So we're gonna put you in breakout groups for 7 or 8 minutes, and then we'll come back just for a brief closing. But yeah, thank you so much for your time. And yeah, you should be in breakout groups shortly. So go ahead. All right, I might just close by summarizing some of the things that came out of the group discussions in our group. And I'll focus on the next steps because really that's what we hope you can leave this meeting with. I think there was clear direction about having pilot projects. Maybe not focusing on critical infrastructure, but something small, and really more internal work at agencies to learn about if this is allowable in current specs. I think people were still a little bit unclear about that, so a little bit more work there. I'm seeing on group 2, folks want to see more existing demonstration projects and case studies. That is certainly a challenge, and I think we can do more work in pulling from other countries where this is a more established material. So certainly we can do that. And then I think this group was focused more on the challenges, but I think it looks like there's a lack of studies, data to demonstrate the workability of LC3. And that's something that our group talked about as well, is just more information on the performance characteristics of the material. So thanks for participating in this workshop. We hope you found it useful, and we'll be sharing the slides, and happy to take any follow-up questions via email. I think you should all have our contact information, but we can include it in our follow-up email as well. So thanks everybody, and have a good rest of your week.